Long before the automobile existed, humans dreamed of flying cars. We have planes that can break the sound barrier, helicopters that do backflips, and drones that deliver your takeout. And yet, no flying car. Why?
Here's the twist. Flying cars kind of do exist. They're just not cars. They're called eVTOLs, electric vertical takeoff and landing aircraft. They lift off like helicopters and cruise forward like airplanes. The key word is electric. Unlike traditional aircraft that burn jet fuel, eVTOLs run on battery power, making them significantly quieter, mechanically simpler, and far more environmentally friendly.
They're designed for short-range urban trips, airport transfers, cross-city commutes, and rapid emergency response. Think of them as the next evolution of rideshare, but above traffic entirely. Among the most compelling early use cases is emergency services. An eVTOL can reach a hiker stranded on Camelback Mountain or a cardiac patient in gridlock traffic in a fraction of the time. That speed saves lives.
So, how does an eVTOL actually fly? It comes down to a concept called DEP, distributed electric propulsion. Instead of one massive engine, which is a single point of failure, DEP uses multiple smaller electric rotors spread across the aircraft. If one motor fails, the flight computer compensates by redistributing power to the others.
The power source is a high-density lithium-ion or solid-state battery pack. Vertical lift demands a huge burst of energy and generates serious heat, requiring rigorous thermal management systems. Once airborne, a centralized flight computer acts as the brain, processing data from LiDAR, radar, and GPS in milliseconds to maintain stability through redundant flight controllers. The engineering works, and universities are the foundation. Research programs at MIT, Stanford, Georgia Tech, and ASU are actively advancing battery chemistry, autonomous flight software, and urban airspace modeling, feeding a pipeline of talent and breakthroughs directly into this industry. But building one aircraft is very different from building a transportation network.
But here's what's easy to miss. None of these systems work in isolation. An eVTOL isn't just a battery, flight computer, plus some rotors. It's a fully integrated stack where every component has to speak the same language, in real time, without fail. Battery management talks to the thermal system. The thermal system informs the flight computer, and the flight computer reads LiDAR, radar, and GPS simultaneously, cross-checks with navigation software, and adjusts all 12 rotors in the same millisecond. On top of that, human factors engineering shapes every interface so that pilots, and eventually no pilots, can trust the system under pressure. This is called multi-channel integration, and 10 years ago, it simply wasn't possible. The sensors weren't small enough, the processors weren't fast enough, the software couldn't run it, the batteries couldn't power it. The convergence of advances in material sciences, computing, and aerospace happening all at once is exactly what makes this moment different from every previous attempt.
And no single company, no matter how well funded, can advance all of these fields simultaneously. That's why university research isn't a nice to have, it's the foundation. Battery chemistry breakthroughs come from material science labs. Autonomous flight algorithms emerge from aerospace and computer science departments. Thermal modeling, structural analysis, human factors. Each of these has a research lineage that predates the eVTOL industry by decades. The industry didn't invent these fields, it inherited them. MIT, Stanford, Georgia Tech, ASU. These aren't just training the engineers. They're producing the underlying science that no startup can afford to fund and no market incentive would support at early stages. Basic research doesn't have a product timeline. That's precisely why it needs universities, and why federal investment in those programs isn't subsidizing an industry. It's building the knowledge base the industry runs on. For a century, the answer to urban congestion was more road. And every time we did, traffic expanded to fill it. A phenomenon so reliable that transportation planners gave it a name, induced demand. The road created the trip. We built our way into a trap. Meanwhile, the first 1,000 feet of air above our cities remained almost entirely unused. Barely any cargo, almost no passengers. Just empty sky sitting above gridlocked roads. Helicopters hinted at the solution, but the noise, the cost, and the mechanical complexity meant urban planners never seriously considered them at scale. So the airspace stayed empty. eVTOL is what finally changes that equation. Quieter, safer, simpler, and built from the ground up from our cities. The idea was always right. The technology just had to catch up.
The race is already underway, and it's further along than most people realize. Joby Aviation, backed by Toyota and Delta, has logged hundreds of test flights and is targeting commercial launch in the coming years. Their partnership with Uber, which is already live in Saudi Arabia, allows for users to call a ride through the app. Additionally, Archer Aviation's Midnight aircraft recently completed full-scale piloted flights. Wisk Aero, backed by Boeing, is pushing the technology even further, developing a fully autonomous air taxi that requires no pilot at all. The competition is global and it's accelerating.
So, the engineering works. The prototypes fly. But how does this actually roll out without becoming the next overpromised transportation revolution that never quite arrives? Start with geography. In New York City, roughly a quarter of all days bring weather conditions that would ground eVTOL operations: wind, ice, low visibility. In Los Angeles, replacing even a fraction of car trips would require not dozens of aircraft, but hundreds of thousands. And then there's the question of interoperability. When Joby, Archer, Wisk, and Airbus are all flying vehicles over the same city, how do they communicate? They don't share a radio frequency and hope for the best. The answer is UTM, Unmanned Aircraft System Traffic Management. The FAA is building this framework now. Standardization isn't optional. It's the prerequisite for the whole system to function safely. The honest path forward is phased. Start with lower risk corridors, airport transfers, suburban medical response, routes with predictable weather windows. Prove the safety record. Build the vertiport infrastructure incrementally. Let the regulatory framework harden around real operational data, not projections. Scale only as fast as the evidence supports.
Getting eVTOLs off the ground legally is as complex as the engineering. The FAA must certify each aircraft design, a process that typically takes years. In 2023, the FAA released its Advanced Air Mobility Implementation Plan, creating the first regulatory framework specifically for eVTOL operations, a meaningful foundation that grows more detailed with every passing month. At the federal level, NASA's AAM mission has poured tens of millions into research, with over $22 million alone going into universities to improve VTOL technology. The DOE, through their ARPA-E's Scale-Up program, has invested over $20 million into energy storage, which is exactly what eVTOLs will need to succeed. A recent executive order on American drone dominance signals that the government sees this as a strategic priority, not just a transportation upgrade.
Meanwhile, states aren't waiting. Arizona's governor launched an AAM working group and designated Sky Harbor as a future vertiport hub. Phoenix is positioning itself as a proving ground for the next era of aviation.
Building the aircraft is step one. Building the ecosystem is the real challenge, and that ecosystem comes down to three things, an acronym that couldn't be more fitting: AIR. It starts with the aircraft. Batteries need higher energy density and faster charging without compromising thermal safety. Flight software needs to be proven at scale, not just in test conditions. It continues with the infrastructure. You need vertiports, not helipads. Think mini airports, multiple landing pads, fire suppression designed for lithium battery incidents, as well as megawatt level charging that can turn around an entire fleet in minutes without knocking out city power grids. Above them, a UTM, Unmanned Aircraft System Traffic Management, a digital air traffic control layer that choreographs thousands of low altitude flights in real time, deconflicting routes, integrating weather data, and hardened against cyber attacks. Then come the rules. The FAA has to certify every aircraft design and every vertiport location. Insurance and liability frameworks also have to stabilize. And perhaps hardest of all, public trust. Trained pilots, transparent safety data, and communities that believe this system improves their lives rather than disrupting them.
History has a pattern. The hardest part of any transportation revolution was never the vehicle. It was everything else. The car existed decades before highways, traffic laws, or gas stations made it practical. The airplane flew in 1903, but commercial aviation didn't become ordinary until the 1950s.
eVTOLs are somewhere in that middle stretch, and that's actually the most exciting place to be. The physics work, the prototypes fly. Real passengers have ridden in certified aircraft. The FAA is writing rules it's never had to write before. Cities are redesigning rooftops. Universities are training the engineers, planners, and pilots who will operate this system. Billions of dollars are moving towards a single bet that the sky above our cities is the most underused transportation resource on the planet.
So where is my flying car? We're watching it get built, certified, and cleared for takeoff in real time. The batteries will get better, the software will get proven, the routes will get cheaper. That's not optimism. That's just what happens when this much talent and capital chase the same problem. So we'll be here,
The only question left is how soon.